It is now my pleasure to introduce our guest speaker, Dr. Muhammad Hamad Rasool. Dr. Hamad Rasool is a petroleum engineering scientist and currently serves as a postdoctoral researcher at University Technology Petronas, Malaysia. His research integrates drilling engineering, geochemistry, and sustainable subsurface energy system with strong focus on drilling fluids, geological CO2 storage, and critical mineral recovery. He is ranked among the top 10 petroleum engineering scientists in Malaysia according to the AD Scientist Index 2026. And he is a registered professional technologist in oil and gas in Malaysia. His work includes eco-friendly drilling fluid additives, caprock integrity assessments for CCS applications, and evaluation of secondary rare earth resources. Please join me in welcoming our guest speaker, Dr. Muhammad Hamad Rasool, to present cement design for CO2 storage wells. Dr. Hamad,
Okay.
floor is yours now.
Thank you so much, Sir Asif and Dr. Gima, for your kind words. So, the topic for today's workshop would be cement design for CO2 storage wells, as Dr. Gima already mentioned. This topic must be very interesting for the well engineering students because CCUS is something that is currently a very hot topic in energy solutions and also in climate mitigation strategies. I can see we don't really have a lot of students, but we have a few. But one thing that I want to say first before we proceed um, formally, I want to make this session interactive. Uh, if students feel a little bit shy, you don't really have to say anything on the microphone. You can just type. So we can communicate through typing. I know it's Gen Z. Gen Z kids are kind of shy, so I'm not really going to ask you to come to the microphone and talk. But if you want, that's appreciable. But if you don't want, you can just type. So I'm just going to share my screen first. Mm, Just give me a moment. Am I audible and is my screen visible?
Yes, Dr. Muhammad Hamad, we can hear you properly and your screen is visible to all.
All right, thank you so much for the affirmation. So the topic for this workshop that I will be conducting today will be semen design for CO2 storage wells. Before we officially talk about the semen design itself, I want to talk a little bit about the CCUS. What is this CO2 storage and why do we even need it? So after the end of this workshop, the students and the audience will be able to know the fundamentals of the carbon underground storage. They will be able to learn the API semen classes and their application in well engineering. Moreover, they will understand how the semen provides zonal isolation and they will recognize why CO2 environment is corrosive and usual Portland cement is not really an ideal solution in CO2 storage environments. And moreover, we'll be talking about various classes and various advancements in acid-resistant cements that is currently being studied in the literature as well as in the industry. But first thing first, why CO2 storage is not optional? Because with the advancement and in industrialization, the global CO2 emission has been increased to uncomfortable numbers. And there are some sectors like cement industry, steel industry, no matter what we're going to do, they're always going to produce carbon dioxide. So even with the aggressive renewable sources, like net zero is mathematically not possible if we do not do anything with already existing carbon dioxide in the atmosphere. So the conclusion is pretty simple. If CO2 is not stored underground, it's going to stay in the atmosphere. And if it is in the atmosphere, it's going to cause a lot of problems like acid rain, global warming, ocean acidification, and a lot of things that we do not want for our beautiful Earth. So now, at this moment, many of you guys might say, why don't we just reduce the emission? The thing is, carbon dioxide is already present in the atmosphere and is already heating the atmosphere. And there are some industries which we call hard to abate sectors, like steel industry, refining industry. No matter how much restriction we put, they're always going to produce carbon dioxide. If we introduce carbon storage or CCS in it, it will immediate do the emission reduction, and it is compatible with already existing infrastructure. So what is this CCUS? Uh, Carbon capture, utilization, and storage. Capture is something that is mainly dealt with chemical engineers. What do they do? They capture the carbon dioxide directly from the air, which is called direct air capture, or they can capture it from the pre-combustion or post-combustion processes using different membranes, solvents, or different kind of substances. But as petroleum engineers and you being well engineers, to be honest, this is not your concern. What we are really concerned with is the carbon dioxide storage. By the way, utilization is something they take CO2 and they just convert into something that is useful, maybe feedstock for the next industrial process, maybe to make methanol, ethanol, or some useful products that we can use as catalysts or solvents as well. As petroleum and well engineers, the one thing that we are directly concerned and that is relevant to us is carbon dioxide storage. It is also called carbon dioxide sequestration. In simple words, you take the carbon dioxide from the atmosphere and you just directly insert it underground. So why do we actually call it geological? Because we're using the Earth's own natural containment system. For millions of years, Earth has already these fluids and gases trapped inside it. So why don't we engineer this underground space and store this carbon dioxide in it? Now, there are various options to store the carbon dioxide. We can store that carbon dioxide in deep saline aquifers. Aquifer is like just a water body underground the surface, which is trapped by an impermeable formation. We call that impermeable formation as cap rock. And then we can already use the utilized one depleted oil and gas reservoirs. Once they have been produced, we can re-engineer them. We can retrofit them to inject the CO2 because they already have traps. They already have this cap rock. We can use igneous rocks, mainly basaltic formation, which provides a very permanent sequestration method. We can mineralize carbon dioxide, and it is one of the most permanent carbon dioxide sequestration solution, but it takes centuries and it hasn't been really proven yet. We have proofs on the lab scale, but on the industrial scale, it's not really quite something we rely on. Or we can use the shallow coal seams, which can be used for ECBM, enhanced coal bed methane recovery. I'm going to talk a little bit about all of these first before I formally talk about the cementing system and why cementing design must be a little bit different in CO2 storage environments. So what happens in saline aquifers? We have a water body that is trapped with a cap rock. Cap rock is an impermeable formation. So when you inject CO2 in it, it is injected in supercritical form. So the primary containment mechanism is structural trapping. You have a structure and the CO2 won't be able to get out of this structure because it is impermeable. The second mechanism it could be the CO2 can just be dissolved, can be soluble in this CO2. This is called solubility trapping. It kind of makes carbonic acid. So next one, we can talk about the storage in depleted oil and gas reservoirs. So once the oil and gas or the hydrocarbons has been produced, we already have traps or empty spaces in the formation. So we inject the CO2 in the formation. Since it is trapped with a cap rock, it could be shale, maybe a mud rock, or a tight sandstone, which is quite rare for a cap rock, by the way. So this CO2 would be trapped underground the surface. And this term that we use in the literature for CO2 volume that is trapped is called CO2 plume, which is basically the volume of CO2 that we trap inside the formation. Second last but not the least, is the igneous rock. Uh, What does it do? We take carbon dioxide, inject it in any igneous, maybe mafic or ultramafic rocks. The one that is really popular is basaltic formation. Basalt has reactive minerals. For example, it has pyroxene, plagioclase, olivine, which are rich in magnesium, calcium. So what does it do when you give it proper reactive atmosphere, like you have brine, you have excessive supply of calcium ions, magnesium ion, a proper pH. So the reaction happens, though it's going to be very slow, it's going to take a lot of time, and you will make a carbonate. For example, if you have plagioclase, which is rich in calcium, you get calcium carbonate. If you have olivine, which is rich in magnesium, you get magnesite or magnesium carbonate. So depending on the type of minerals you have in your basalt, so this process is called in situ mineralization, the mineralization that is happening inside the reaction environment. Last but not the least one is ECBM. You have coal bed seams in the shallow depth. So this is actually a win-win process because CH4 is trapped inside those coal seams. So once we inject carbon dioxide in those coal seams, what will happen? We're going to have two good things. The CO2 that we do not want will be stored in those coal seams. And as the result of that, we're going to get CH4 recovery. We call it enhanced coal bed methane recovery, ECBM. But obviously, this is not something today's topic is about. This is more about the background of the whole problem. So now let's talk about the cementing system. But before we talk about it, I'm going to tell you how many cementing jobs we usually classify the cementing into. So we can have two type of cementing system or cementing jobs. The primary cementing system is something that we are already well aware with. This is something we use for the well construction. This cementing is done between the casing and the formation, and it places a continuous cement sheet between the annulus and the casing. So it provides zonal isolation, stability, and consolidate the wellbore. And moreover, we have remedial cementing, which is done after the primary cementing is done. It is usually for correctional purposes. So what do I mean by correctional purposes? Maybe for abandonment preparation, maybe for plugging preparation, maybe you have some zonal isolation, maybe you have microannulus. So you have a target zone that you want to target on the later stage. So we go for remedial cementing. The purpose is same. We're doing cementing to ensure the long-term well integrity. Before I tell you how does a cementing system work or how does a typical cementing job looks like, I want you to look at this very simple, very easy to follow schematic. So the mud is coming from the mud pit and then the standpipe. You will see the casing, the green one, is already installed. So once the casing is already there, the mud will by default enter into the casing. You see the centralizers whose main job is to keep the casing in the center of the wellbore. We have a casing shoe as well, which kind of provides or avoids the U-tubing effect. It won't let the mud to flow back inside the casing. So it's only kind of allowing the one-way flow. So moving on, now we're going to start the cementing job and it's going to be very interesting. So firstly, what will happen? We are not really going to insert the cement right away because cement and mud are not chemically compatible. Let's say if we insert cement right away, we are going to get a gelation, a type of gel structure which won't be easy for us to remove. So what we do, you see, there are three things between the mud that is already present in the casing and the inserted cement. We have a bottom plug, which is sitting behind the bottom. We have a spacer fluid, and we have a washing pre-flush or post-flush or chemical wash. The purpose of the chemical wash is to make sure to wash the wellbore and the casing surface because we want to have a good interface for the casing as well. So the bonding between cement and casing sticks. If it is not cleaned properly, the cement might make a microannuli. This is something we do not want. And the purpose of the spacer fluid, which is controlled by density, the main purpose here is to keep cement and your mud separate. Chemical wash is not really controlled by density, and it is not really quite are recommended or not quite very important when you are using water-based mud. But when you're using oil-based mud, it is imperative, it is inevitable that you're going to use a chemical wash, because if your casing is oil wet, the cement is not really going to set, because your cement is water wet by default, right? So we're going to use chemical wash in either scenarios, water-based mud or oil-based mud. But in oil-based mud, it is highly recommended, and its composition would be very aggressive when we talk about oil-based mud. Okay, now let's see what happens. Obviously, we're pushing the cement slurry inside. So now behind the cement slurry, we have a top plug, which is going to guide the cement slurry, and we have a displacement fluid, which can be the active mud that you're currently using in your mud circulation system. So this displacement fluid is going to push, push, push. This top plug will come. It is going to push the slurry down until and unless when you see this cement slurry will exert pressure on this bottom plug. Now this bottom plug is rupturable. If you're going to apply a lot of pressure in it, this will open, it will tear apart, and the cement will start moving from this bottom plug, from the casing shoe to the annulus. And it will keep on moving down, or the displacement fluid will keep on going down until and unless the top plug will sit on the bottom plug. So this is how the final complete job looks like. Now, at this point, for the students, if you're wondering, okay, we have done the cementing job. Now we have to drill the next section. So what's going to happen with this shoe? What's going to happen with these top plugs, with the bottom plugs? So I know it's something that you might be wondering about. But the thing is, they are drillable. They're not really strong steel. They're made of like polymer or plastic type of substance, which can easily be drilled. So you don't really have to worry about it. They have done their job. They have done their task. So now the cementing system that we use is not really one type. We have 9 different classes of API cement ranging from class A to class H. Now, literature might divide these classes based on depth. For example, if they say you have 6,000 feet, you use class A, but that's not right. Because in literature, you will find different depths for all these classes. The real utilization or the real definition would be they depend on bottom hole circulation temperature and bottom hole circulation pressure. So based on those things and other some certain condition, when you have hydrogen sulfide, you can use any of these classes. But the usual or the by default one that we use in oil or gas well drilling for HT/HP condition is class G cement. And when we talk about research, class G cement absolutely makes a best base to add more additive in it to see the effect of additive in the cementing system. We call this cementing system as Portland cements. This is something that we use in oil and gas industry. And again, to conclude, class G cement is something that we use in our by default or conventional oil well cementing. So now I'm going to talk about that why this class G cement is something that is not really suitable for CO2 storage well. But before that, we need to understand why this CO2 storage environment is corrosive. So on your slide, you see a very typical CO2 injected system and a cased well where the cementing job is done. You see intermediate surface conductor and you have production casing as well. Maybe we can say this is like a depleted oil and gas reservoir, which was abandoned. So we're going to use the same abandoned well to inject CO2 in it. Now, if it is being injected, there is a CO2 plume in it. So CO2 has this buoyancy in it. It will start to rise above. Obviously, this confining layer or cap rock is going to stop its migration or leakage. But let's say, what are the possible scenarios this CO2 can leak through this annulus and can cause problem for us? It can leak from multiple ways and multiple pathways, from casing and the annular cement, between the cement plug, through fracture, through the casing, and between the annular cement and rock. So in other words, the possibilities are unlimited, limitless. So now once the leakage start, I'm talking about class G cement now, things won't go right. Things might go south because our CO2 storage environment is very corrosive. corrosive. Why it is corrosive? Why it is too acidic? Because when we inject CO2 in brine formation, brine is already present as formation fluid. It is going to make carbonic acid. Now the whole environment become rich in acidic, right? And you have high temperature conditions as well. So it might corrode your cement and steel as well. I want to give you a view of the chemistry behind it because this is very important that you understand the underlying chemistry to build your solid or other hypotheses and solutions on it. Without the chemistry, this stuff won't work, trust me. So first step first, you inject the CO2 and it is going to dissolve in the formation brine. So this will be soluble based on Henry's law, which talks about the solubility of gas. So this gas and the aqueous CO2, which you injected in the formation brine, will be in equilibrium. Now, once CO2 is in equilibrium, it is in aqueous state. It is going to react with the formation water and will give you carbonic acid. So carbonic acid is not really stable, so you will see a reversible chemical reaction here as well. So obviously now the carbonic acid will dissociate, give you the first proton, and this release H plus ion will lower the pH, and the whole atmosphere will keep on becoming more and more corrosive. Okay, now what happens? Now we already established that our CO2 storage environment is very corrosive. It's very acidic. Now what happens to our good old Class T cement? So let's say I'm doing my usual oil well cementing and I'm going to use a Class T cement for my CO2 storage well. What can go wrong? So these Class D cement, let's talk with the equation first. I mean, this is more suitable at this point. So the typical chemistry of these API cement is this calcium and silica. Class G is rich in tricalcium silicate. Tricalcium silicate. So what will happen? The first thing first, this tricalcium silicate will undergo hydration, react with water, react with H plus ions, and it will form a substance which is called portlandite. Portlandite, which is basically your calcium hydroxide. So this calcium trisilicate reacts with water, and again, in the start, obviously, when you cement water the cement, you get an initial strength. So cement gains initial strength via calcium, silicon, hydrogen bonding, but at the same time, as a byproduct, you get this product which is called calcium hydroxide. Now I'm going to tell you what is wrong with this calcium hydroxide and why is it something that we do not want in our well. Again, the previous process is that you get carbonic acid. Now this carbonic acid that was produced in the start, it is going to react with carbonic acid and you will get calcium carbonate. And we know calcium carbonate is brittle, it can crack down, it can cause a lot of permeability, porosity, which will undergo and make our cement system susceptible for CO2 to migrate through it. And also, more and more calcium carbonate will react with CO2 and will give you calcium bicarbonate. And at the end of the day, what will happen? All of the calcium ions which were present in your cement system and which are responsible for the strength of your cement system will start leaching out. Your cement is actually losing strength. So it all started with the formation of this culprit chemical, calcium hydroxide. So this calcium hydroxide react with more and more carbon dioxide, give calcium bicarbonate, and this bicarbonate will cause more and more leaching of calcium ions. Now let's talk about the solution. So obviously we have established that the current Portland system is not really suitable for CO2 storage environment. So what are the possible alternatives? So we have two possible alternatives that is currently being utilized in the industry as well as in the research and literature as well. We can modify the Portland system. For example, we have Class G, right? So we add different additives in it. The one that is very popular is pozzolanic cement. In pozzolanic, you have silica fumes, fly ash. They're literally the part of pozzolanic cement. So why pozzolanic and what do they actually do? So when we add a huge amount of fly ash or silica inside our Class D cement, it lowers the calcium to silicate ratio. Because in our Class D cement, it has a huge amount of calcium. But if we add silica, The lower calcium to silicate ratio will produce a very small amount of Portlandite. And if calcium hydroxide is less calcium carbonate will be formed. So we won't really be worried about the leaching of calcium plus and losing the strength, because these additives are not really dependent on the the Portlandite system as well. And we have metacholine as well. Metacholine also is one of the pozzolanic substances that we can use. The other system that we have is not to rely on the Portland system at all. We call them non-Portland system. You might have heard about geopolymer system, which have a huge amount of fly ash and alkaline activators. And we have magnesium phosphate cement, which do not depend on tricalcium silicate at all. We might have calcium aluminate cement, and they have high alumina calcium, and they make little to less Portlandite, because in all of these systems, they do not have tricalcium silicate, which was the main reason to produce Portlandite or calcium hydroxide. Or we can have hybrid cements, and we have nano-engineered cements. Now they're using nanoparticles in your cement slurry as well. Or you can have carbide soil systems. So these are some of the examples of our cement systems that we may classify in the non-Portland cement category. So this is the part of our review work. What we did a comparison from 100 plus studies. Some people have used latex modified Portland, silica modified, nanosilica modified, CAC, and geopolymer. So our studies showed that, okay, all of these classes gave better results as compared to Class G or conventional Portland cement. But among all of these classes, calcium phosphate cement was the one which gave highest compressive strength after being exposed to acid. Carbonation depth is one of the parameters that we measure for our cement and acid exposure study. Carbonation is basically the depth of calcium carbonate formed on your cement after reacting with acid. So you see, among all the cements we studied, calcium aluminate cement gave the minimum carbonation depth. The main mechanism behind it, it doesn't have the typical tricalcium silicate network. It has calcium alumina network. So it makes calcium aluminate hydrates, not calcium hydroxide. So Portlandite is not really a problem. So we don't really have to worry about the strength issues and other things as well. Now, this is a very typical cement recipe, which is followed by API 10A1 that we usually use to make in the labs or as well as in the industry. But before I talk about that, I'm going to tell you two things that we utilize in the literature. The one terminology is called by BWOC. It's called by weight on cement. So all the additives that you use are related to this weight on cement. For example, in this scenario, the weight of the cement is 100% if we take. So the water, the dispersion, the fluid loss additive, the retarders, the deformers that we're going to utilize in our mud slurry or the cement recipe are based on this. The second thing that I want to tell you, whenever we make a cement system in the mud, we can customize it, of course, based on our well requirements. The one thing that we always take care of is water to cement ratio. Water to cement ratio is very important because it kind of dictates how the microstructure or how the reactions are going to be controlled. If it is too much, then the rheology would be affected, the slurry pumpability would be affected. If it is too low, it won't be able to move. Uh, so there are a lot of things. Now, in this scenario, and according to the APA recommendation, if you look at it, the weight on cement is 100%, while the added water is 44%. So can you just do the quick maths in your mind? You don't have to say anything, you don't have to write anything, and can tell me or tell yourself, what is the water to cement ratio in this slurry? So if you have done the maths, the very simple math, you will see the water to cement ratio is 0.44, which is actually the default cement to water ratio, water to cement ratio. that we use in the literature or for the base composition. And it is recommended by API as well. But this is not something that is a fixed point. It can be changed as per the requirement as well. Also, one thing that we introduced as a part of this study in our review paper, there wasn't any particular protocol that we can follow for the lab testing for the CO2 exposure tests. So we introduce a phase-wise lab testing protocol for CO2 exposure study. So in the phase one, once you have formulated your semen based on that formulation, you can perform your rheology testing, which is definitely just like the one that you do for drilling mud. You can do the setting time analysis, like by which time the cement is setting. You can have a free water test, that how much water is uh, left or stranded or suspended. You can have a sedimentation test and compression test. And in the phase two, we go to the next level. We have this thermal curing. We cure it at high temperature. We study its strength with the passing time. We can study its thermal analysis. We can do its calorimetry, and we can do XRD. Now, phase three, we expose it to the acid. The exposure to the acid is usually done in autoclave, but this is very interesting. Now, for CO2 storage study, what kind of acid do we need? Think about it. We need carbonic acid. Now, I'm going to ask you something. You don't have to answer, just think in your mind. Can you buy carbonic acid from the lab? You can buy HCl, you can buy sulfuric acid. Of course, you can, if you have sulfuric acid, you can just dip your cement in it and study it if it is degraded or not. But can you buy carbonic acid, which is the main culprit, and it comes from CO2? You cannot. Because carbonic acid is not stable at all. It only exists in equilibrium with carbon dioxide when proper temperature and pressure conditions are met. So we use this thermal curing autoenclave. We provide carbon dioxide atmosphere, and this immersion test can be done. And we can measure the compression pre and post exposure so that we can compare how our new mud system has behaved in after or pre-exposure to the acid. You can have buffering index and pre and post exposure. The phase four is just for the advanced level studies. If you really want to go to the next level, you can have permeability testing, you have micro CT, you have gas fluid migration, you have tensile strength. So just I want to put more emphasis. So in our study, what we have found out that calcium phosphate cement, calcium aluminate cement, or calcium phosphate cement is something that is the topmost so far, and it is giving the best results possible. I'm not really sure if it has been adopted by in the industry yet, but in research, we are currently focusing on calcium aluminate cement, and we're adding different additives in it to see how much it is performing. We're not really relying on the Portland cement, and we're not really adding any additive in the glass cement as well. So this was basically it. So I think I gave you the basic idea how the cementing system worked for CO2 storage well. Now I have really something really excited that will involve you guys as well, because I told you that I want to involve the audience as well. So we have 11 people. Mainly I want to target the students. Oh, we have one Hamad as well. Oh, we have two Hamads. So including me, we have three Hamads now. So we're going to have a little bit discussion on what we have just learned. I will show one simple question or one simple concept that we just studied, and you try to answer it. Everybody is welcome to answer in the chat. So we'll discuss more on it. So the first one, let's talk. So if a semen sample gains compressive strength after carbonation, so when I was talking about class T cement, I told you calcium carbonate is formed. When calcium carbonate is formed, it will give it strength, because calcium carbonate is like a protective layer, a protective extra phase. It is going to give it strength. So does that mean if that calcium carbonate is formed, does that mean it is performing well in a CO2 storage well? What do you think? So do you think it is something that we want in a CO2 storage well? You can just write your answer in the comment, and then we can have a discussion on it. What do you think? Do we need calcium carbonate? Because I told you it is giving early strength to your cementing system. You can write yes or no. I mean, I just want to see that. What are you guys thinking at the moment? When calcium carbonate phase is formed, do you think it is something we want for our CO2 storage wells? Because we know calcium carbonate will give early strength to the cement. Do we want it? Yes or no? You can just type it. So what do you guys think? Do you think calcium carbonate? You can say yes or no. Okay, if not, I think I'll just tell you. So that's true. When calcium carbonate is formed, it is going to give you early strength. But remember, after some time, it is going to leach out that calcium. It is going to be very permeable, very porous. So this is something we do not want in our CO2 storage wells. So yeah, this is not recommended at all. But for the next one, I hope somebody will try to contribute in the discussion. Okay, which is more dangerous for long-term CO2 storage containment? High permeability or low compressive strength? Okay, that's correct, Hamad, because I think your name is Hamad, so you would be absolutely right. So yeah, because for compressive strength, we can kind of like make an exemption, but for the permeable, in CO2 storage, the most important thing is containment. We do not want our CO2 stored to leak from the places. So that's absolutely right. Very good, Hamad. We do not want a hypermeable system that is more dangerous for CO2 storage.